Welcome again to my mathematics online tutorial. And in today's class, we still want to discuss what mathematics can do lesson 3 or lecture what? 3. That is, we want to formulate a mathematical model for the spread and control of COVID-19, which we also call coronavirus disease. I've been telling us that mathematics has gone beyond the level of finding S and Y. And even if we find S and Y, what do we use the S that we have found to do? So nothing. That is why I'm here to tell us again that mathematics has gone beyond that level. And in today's class, we want to formulate a model for what? COVID-19 and how it spreads and then the control. Now, I have we will now start from the model flow diagram, which have susceptible, the exposed, the infected, the recovered, the what's it called? The vaccinated, the quarantine, and the isolated. But before then, what is COVID-19? As you all know, COVID-19 is a respiratory disease that is majorly transmitted via respiratory droplets. And these droplets could be in form of when an infected person sneezes, talks, or even coughs. And that is why it's advisable that we maintain social distance. That is, when someone that is infected with COVID-19 coughs, sneezes, or even talk, they release droplets that could cause the COVID-19. And now we want to formulate the model. Follow me now and see what mathematics can do. Now, the susceptible population, they don't have the disease. The exposed, they are infected but not yet infectious. The infected here, they are infected but infectious. The recovered, the vaccinated, the quarantine, and this place is what? They are isolated. We isolate them for treatment. So let us assume that this population grows at the rate of what? Lambda. We call it the recruitment rate. All right? The recruitment rate. And now for an exposure to occur, the susceptible person must have contacted the infected. That is, there must be a close contact between X and I. And that is why we have something like beta IX here. So that is for an exposure to occur. For this person to be exposed, the susceptible must have a contact with what? The infected at the rate of beta. All right? Now, the exposed becomes fully infectious after some times. They become what? Fully infectious, maybe at the rate of, let me use alpha 1E. After some times, they become fully infectious, and then they move to the infected but infectious and also infectious class. And they can recover naturally without, what's it called, treatment. Let's assume that they recover naturally without, let's say, gamma 1I. We attach I here because this is moving from the I class. We attach E here because it's moving from the exposed class. And look at the exposed now. The difference between this exposed and infected is this one is unconfirmed cases of COVID-19. But here they are confirmed. So for those that are not yet confirmed, we take them to the quarantine center. We quarantine them for diagnosis. And if the test comes out to be positive, Positive, they will now take them for what? Isolation. So let's quarantine them maybe at the rate of theta sub 1A. And then this is confirmed cases. So we take them directly for what? Isolation. And when they are isolated, it's at this point that we treat them. So maybe theta 2I. All right? Now, the quarantine, those that are confirmed to be positive, that is, the positive cases are taken to what? Isolation center for treatment. So permit me to use alpha 2 now, alpha sub 2Q. We attach this Q because it's leaving the quarantine center. Now, these people, they isolated for treatment. No, they recover. They can recover. Let's call it, that is recovery due to what? Treatment. So let's call it a gamma 2J. Look at this one. Gamma 1 means natural recovery. But this one is recovery due to treatment from the isolation center. So this recovery is always higher than this one because these people are receiving treatment. And now, as also part of the control measure, remember the quarantine is a control measure, the isolation is also control measure, and the vaccinated is also a control measure. But we vaccinate the susceptible population, people that have no disease, we vaccinate them against the disease. Now, let's assume that we vaccinate this class at the rate of omega 1x. When the vaccine fails, they return back because there's all possibility for the vaccine to what? To fail. So now say omega 2v. If it fails, they return back. And now, the vaccinated, when the vaccine did not fail, if it works, these people will now develop, they will now recover. They have permanent immunity. Maybe they recover, they are taken to that class. Maybe let me use omega 3, that is V now. And you know, the fact that you recover from a disease today does not mean tomorrow you will not get it. So the recovered again can also become susceptible again if care is not taken. That is, they go back to be what? Susceptible. So let me use here to be omega R4 because we have omega 3. Omega 4R. All right? So, and we have what we call the natural death rate. These people can die naturally. So let's use mu X. The exposed can die what? Naturally. Mu E. Now, the infected can die two ways, either by natural death or by the disease because they are infected. So let me use, let me say pi 1 should be what? Disease-induced death. That is, if COVID-19 kills you, we call it what? Disease-induced death. Then the natural death is also there. You can also die naturally. So mu I. Also here again, those that are isolated for treatment, they can also die due to the disease because they are sick and they are receiving treatment. So let's say pi 2J. And here we call it what? Natural death. All right? Natural death. Now, the recovered again can also die naturally. That is it, but not due to the disease. And now, the quarantine can also die what? Naturally. All right? Natural death. So, okay. And also, the vaccinated can die. The vaccinated can die naturally again. That is it. Then, there's also a control measure that I want to, there's also a control measure that I want to introduce. Now, this is beta IS, where beta is the contact rate between I and S. So, we want to bring in an awareness campaign measure, that is, for the susceptible to keep social distance from the infected ones. So, let me bring something like 1 minus X. Look at it. If we put S to be 0, it means the awareness program does not work. But if S is maybe 0.9, 0.2, because this is between 0 to 1. If it's 0.7, 0.8, it means it works. But when you put 0 here, we return back to beta IS. So let S be an awareness campaign measure for the susceptible to keep social distance from those that are infected with the disease. And this is what we call the model flow diagram. Let's go over it again, because after this, we will now write out the equation and we are done. And when this is analyzed and followed vividly, COVID-19, I know COVID-19 has reduced drastically, but we will not have it again in the country, even in the world. So now, let's check it again to see if there's no any mistake. S, V, Q, all right? Yes, we are done now. So this is what we call the model flow diagram. But here, remember, this quarantine, those that are positive to, what's it called, to the disease are taken to the isolation center. But how about those that are negative? But we assume that everybody that is tested here is what? Positive to COVID-19. If not, we would have taken one arrow again for those that are negative. They would have gone back to the exposed. Modeling is all about assumption. Thank you, and let's write out the equation. What is left now is to write out the equations that correspond to the flow diagram on the board. And the first thing to do is to write that of susceptible class. Ordinarily, we are supposed to say the S, the T. But because of space, let's take the S, the T to be what? S of T like this. Then we put dot. It's the same as what? The S, the T. So I will now be writing. So let me just use, now here, we will say X of T dot is equal to, look at this place. This sign lambda is entering. Then which one is leaving? This is leaving, minus beta I x. Then 1 minus x, all right? Then this is leaving, minus omega 1 x. This one is entering, plus what? Omega 2v. Then this one here, omega sub 4r is entering from the recovered class. So it will be plus omega 4r. Then the last one is natural death rate for this class is leaving, so minus mu x. So this line of equation represents dynamics for the susceptible population. Now, let's move to the exposed class. So it's going to be A T like this. We'll put dot at the top to represent change in exposed population over time. Now, this one, beta IS 1 over S is entering. So it's going to be what? Beta IS 1 minus S, all right? Then this is leaving, minus theta 1 E. This is leaving, minus alpha sub 1 E. And then this is leaving, minus mu E. We are done with the exposed class. We move to the infected class, I of T. This one, look at it. Alpha sub 1E is entering, all right? This is leaving, this is leaving. We now say minus gamma sub 1I minus theta 2I. Then these two are leaving, that is disease-induced death rate and natural death rate for the infected class. So it will be minus pi sub 1I minus mu I, all right? Let's check it again. This one is entering. This is leaving. This is leaving. The two are leaving. Yes, then we'll now move to, let's write the quarantine first. The quarantine, or let's write vaccinated first. Yes, V dot of T, vaccinated population. Now, check very well. Omega sub 1S is entering this class. Then this is leaving, minus omega 2V is leaving. Then this is also leaving, minus omega 3V, all right? Then minus mu V is leaving, that is natural death rate for the vaccinated class. Now, we move to the quarantine class, that is of T is equal to, look at this one, this is entering, theta sub 1 E, this is leaving, minus alpha 2 Q, all right? Then this is leaving, minus mu Q is leaving. Now, we have the isolated class. We use J, T. Now look at it, this is entering, and this is leaving. So we now say alpha sub 2 Q plus what? Theta 2I. Then this is leaving, the minus what? Omega 2J. this is living, that is disease-induced death for the isolated but on treatment class, minus pi sub 2j, then minus mu I. All right? Then let's check it again. This is entering. This is entering. Look at it. This one is entering. It's entering. This is leaving. Yes, we are correct. Then we are now left with the recovered class, because it's 1, 2, 3, 4, 5, 6, and we have 7 compartments. So we must have 7 equations. Now, the recovered compartment equal to, look at it now. This is entering gamma sub 1i, all right? This is entering minus gamma 2j. Then this is also entering plus omega 3v. Then look at it. This one is leaving minus omega 4r. Then minus mu r. As you can see now, we have 7 equations now. 7 will be 1, 2, 3, 4, 5, 6, 7. Yes, which is in line, which is the same thing as the number of, which is the same as the number of compartments that we have from the model flow diagram. And this now represents the mathematical model. All right.